All right, whenever you're ready.
Okay. Well, good morning. This is Andrew Coleman. I am co-hosting today for Dr. Shankar in his seminar series, and I am the executive director for Electric Power Research Institute's government corporate affairs, and formerly a director over at Lehigh years ago. And I'm happy to bring forward this great talk this morning. And we invited Melissa MILSTREY over from MPR Associates. So she's going to be giving a talk for the next hour, and her talk is entitled "Powering Tomorrow: The Commercial Nuclear Power Plant Modernization." So it's great to be part of these seminar series. I try to dial in. I think I'm always about 90% in attendance unless I'm flying around, but a lot of credit goes to Rudy and Susan for putting these on. And it's always great to have a Lehigh graduate come back and talk about the experiences in the work world. And pleased to have Melissa here today. She's going to talk really about maintaining commercial nuclear power fleet and modernizing investments. You graduated right in 2018, right, with the BS in chemical engineering, and Melissa
Yep.
started at MPR. And MPR is a specialty consulting firm which specializes in challenging problems in power and energy, in federal space, life sciences space, and she's been focusing on advancing commercial nuclear power for the last couple of years. And currently, she's a project manager for MPR. She also serves for MPR Women in Nuclear, which is great. And she's the chapter lead. So we welcome you here today. Just a little bit of housekeeping. We have a chat spot. We're going to try and monitor that chat spot and interrupt kindly when we can for Melissa. We kindly ask you to reserve your questions until the end, where there'll be adequate time for Melissa to respond. So we thank all 44 participants coming here this morning. It continues to grow. If you think somebody out there would benefit from this seminar series, just forward on your invitation, because these are all very good opportunities to learn and also to get some inside knowledge from experts like Melissa. So Melissa, welcome. And it's lunchtime, so I'm sure everybody will be this is a good hour for lunchtime, and so I'm gonna hand it over to you, Melissa, and thank you for coming today.
Awesome. Thanks, Andy. Hi, everyone. Excited to meet you all, and thanks for letting me join the ECE seminar today. I'm excited to chat with you about nuclear power plant modernization. Brief overview of what we'll talk about today. First, I'll give some introductions to myself. Andy gave a good overview of that and the company I work for, MPR Associates. I'll give a broad overview of what nuclear power is in general to provide context for the rest of the presentation and the importance of the continued operation of nuclear power plants in the US and abroad. And then I'll dive into modernization, what is modernization, and then some technical examples of modernization that is being implemented in the power industry. And then I'll close out talking with some of the feasibility enablers and challenges for modernization. Then we can have a group discussion and talk a little bit more about modernization as a group. So a little bit more about me. I'm a fellow Lehigh alum, graduated in 2018 with a chemistry degree. I really loved my time at Lehigh and got involved with a number of opportunities on campus. I actually did some Iacocca energy research in UTP, Malaysia. I was looking at different catalysts for hydrogen production. And I did some research also up at Mountaintop with Professor Schultz in a chemie lab, where I was looking at rheology of soft matter. On the more fun side, I was an orientation leader, and I also did tutoring for all 4 years I was at Lehigh with America Reads and America Counts. So shortly after I graduated, I started working at MPR Associates, and I've been there ever since. I'll talk a little bit more about who MPR is and what we do on the next slide. I'm currently a senior engineer, and I've worked for the last 5 years, mostly focused in commercial and advanced nuclear power, and recently have kind of driven deeper into commercial nuclear power modernization, which we'll talk about today. So to give some background on these pictures here, the top one, I'm at a control room simulator at Dresden Nuclear Power Plant. As part of a Women in Nuclear conference, I got to go see this control room simulator and simulate an accident, actually, so that was really cool. And the bottom picture is me on site at an operating nuclear power plant, helping to perform an inspection. So a little bit about the company I work at, MPR Associates. As Andy mentioned, we're a specialty engineering services and consulting firm. And basically what that means is we work on solving challenging and pretty interesting problems for our clients in a variety of different fields. The three main areas that we work in are power generation and energy, which is most relevant to this class today. So we're supporting utilities, including the domestic nuclear fleet. And we also work in advanced energy solutions and T&D, or transmission and distribution of those energy resources. Another one of our business areas is the federal government. So we're supporting government branches like DOE, Department of Energy, and the DHS, Department of Homeland Security, with large scale projects and complex projects. And then lastly, health and life sciences. So this business area is primarily focused in medical device product development. So there's a cool picture here at the bottom of it's called a wound clamp. So there's small needles actually on this clamp that can be used in the field to help close a wound quickly. So, and that one won a design award a couple years back. So we've grown a lot since our company was founded in the 1960s, from 3 engineers all the way up to 200 engineers strong today. So to provide some additional context for the rest of the presentation, I can talk through what is commercial nuclear power and nuclear power in general. Some of this may be common knowledge to some people on the call, but just wanted to provide that overview to the group. So commercial nuclear power plants use the energy released from a fission reaction to heat water into steam. That steam is then used to turn a turbine, and mechanical energy is converted to electrical energy through a generator. A basic kind of flow diagram of this cycle is shown in the bottom left, and you probably have seen this in some of your undergrad thermo classes. So the boiler here and the diagram is equivalent to a nuclear reactor vessel where that fission reaction occurs. The electricity, this output here, that is created in a power plant is then sent to the electric grid, and that's used to heat our homes or power our homes, our stores, hospitals, and even electric vehicles. So what is fission? So you can see in this diagram on the bottom right that the fission is a process where an atom, which is uranium-235 in a commercial nuclear reactor, is split into smaller fission products in an exothermic reaction. So being an exothermic reaction, it's releasing energy, which makes it an effective heat source for generating electricity. In a nuclear reactor, a controlled chain reaction is used. So the reaction rate is controlled through control rods, coolant, and other mechanisms. And that's how heat is generated in a commercial nuclear reactor. So now I'll dive a little bit deeper into the types of reactors that are used in the United States specifically, and then provide an overall snapshot of the US fleet, so how many reactors there are, the life of those reactors, et cetera. It is important to note that there are over 400 reactors across the world. It's not just the technology that's used in the US. And the general modernization concepts that I'm covering today during this presentation are not just applicable to the US, they're applicable across the world. Just focusing in on the US as a snapshot here today. So in the US, there are 2 types of commercial reactors that are used. On the left, you can see a boiling water reactor, or BWR. So this is a schematic of how a BWR works. Basically, water is heated through the reactor vessel and is converted to steam, which turns the turbine directly. So it's called a direct steam cycle. And over here on the right is a figure of a PWR, or a pressurized water reactor, where the water that is heated in the reactor vessel, this orange and red loop here, is used to heat a secondary loop and turn that into steam, which in turn turns a turbine and generates electricity. So that's called an indirect steam cycle, since it has that secondary loop. The U.S. fleet is governed and regulated by an agency called the U.S. Nuclear Regulatory Commission, or NRC, to help ensure that the nuclear fleet operates safely. So the first commercial nuclear power reactors started up about 60 years ago now, I guess, or yeah, in the 1960s. And between the 60s and 90s, dozens of reactors were built all over the US. And it peaked at 112 reactors in the 1990s. Today, there are 93 operating reactors at 54 different sites. And that reduction from 112 to 93 is primarily due to the premature shutdown of some reactors due to financial challenges. There is some good news, though. Vogtle Unit 3 is the most recent reactor that began operation just this past year. So it's a really exciting day for the nuclear industry. And the sister unit, Vogtle Unit 4, is expected to come online this year. So some new commercial nuclear power reactors are coming online. The average age of these 93 operating reactors is 42 years old. So they're getting up there in age a little bit. And these 93 reactors contribute just about 20% of the country's overall electricity. But important to note, these reactors are contributing half of the carbon-free power sources in the US. Nuclear power is unique in that it's always on. It's operating 24/7 to provide that carbon-free energy source. And they're operating at an average capacity factor of over 90%. So it's a good, reliable source of energy for the US. So now I'd like to take a moment and talk about energy trends and predictions for the US. And a major focus in the energy industry, and you probably heard about it through these seminars or other classes, is decarbonization. Specifically in the US, our goal is to shift to 100% carbon pollution-free electricity by 2035. And what carbon pollution-free?
Thank you. No, puppy.
Sorry.
Hey, everybody, if you're
Trying to
attending
listen
and
to
like,
this
if you could put
seminar.
put it on mute, please.
Trying to listen to this webinar. while I-
Okay, we'll try and figure out who to. Susan, maybe we can mute everybody.
I am trying to look. I can't figure it out. I'll keep looking.
So if you could put everybody on mute so we can get through this, but the chat box is very, very much available. Thanks. Sorry, go ahead.
No problem.
It always happens.
It always happens. Yeah, so I was just going to explain what carbon pollution-free electricity means, since it's a newer term. Carbon pollution-free means it can come from energy resources like renewable power, wind and solar, carbon-free resources like nuclear power, and even carbon-emitting resources like fossil fuels that use a carbon capture technology, so it's not emitting greenhouse gases. So this is a pretty major undertaking, a major shift, since we're currently deploying around 40% carbon pollution-free electricity in the US. And as part of that shift, we're expecting to see pretty large-scale closures of nuclear power plants in the next couple of years. Different coal power plants are announcing their closure next year and in the next 5 years. Another big trend in the energy industry is electrification. We've probably all seen there's a lot more Teslas and other electric cars on the road that are replacing traditional gas-powered cars. Electrification provides the opportunity for industrial processes like chemical production, homes, and transportation to be powered from carbon-free resources as a replacement to gasoline and other carbon-emitting sources. So it's really important that the electric grid itself is decarbonized. And you can see that there's this diagram here on the right that shows a prediction for how much electricity demand will increase between now and 2050. It highlights some of the top industries that are electrifying. In blue, that's the transportation industry. In orange is residential, so that's your houses. Industrial is in red, which is chemical plants and others. And then commercial is in green, which is things like offices, office buildings, hotels, and hospitals. I will note that this picture here is a little bit outdated. It's from 2018. So the data is a bit outdated, but I would expect with more current data based on recent industry trends, we'd see an even higher uptick in the potential electrification demand. So overall, since the demand for carbon-free energy is increasing, it will be really important that the nuclear fleet continues to operate to keep the lights on and to help meet carbon goals in the future. So this is a little bit more of a recent projection for energy needs worldwide. So this was a 2023 study by Enerdata, and it shows the anticipated energy demand through 2050. So as you can see, between 2020, 2025 to 2050, the energy demand is expected to nearly double what they are today. So not only will we need to get more capacity for power production and storage, but we'll need to make sure that the carbon-free energy sources like nuclear are maintained to meet those goals. And so that's where modernization comes in. That'll help us to keep the nuclear fleet online and operating to help meet those goals that we talked about on the last slide. So modernization is the use of more modern technologies and processes to help improve the operation and maintenance of various assets. So modernization of the energy sector is becoming increasingly popular over the last few decades. And although it is becoming more popular, the nuclear power plant modernization specifically has been moving at a relatively slower pace compared to some of the less regulated industries like natural gas. It's partially because nuclear is pretty heavily regulated, so it can be costly and timely to make those changes and those modernization improvements. But luckily, we're starting to see a real uptick in the focus on and utility investments in modernization. Modernization in general is a pretty broad term. It can mean a lot of different things, and it can range from actually installing a new piece of equipment or component in a site, or to simply using an iPad for a process that used to be done on paper. So it's a pretty broad bucket of different changes on site. There are multiple drivers for modernization. Some of those drivers include the fleet's age. So as I noted on the previous slide, the average age in the US of the fleet is about 42 years old. So as the fleet ages, equipment obsolescence becomes more of a risk. Equipment obsolescence means that a component or system is outdated and difficult to replace or find vendor support for. And replacing or upgrading to newer, more modern equipment can help to reduce this obsolescence risk. Another main driver is cost reduction. So making nuclear operation cost competitive with other sources like natural gas, which has historically been relatively cheap to produce, or renewables, which are often subsidized. And the third here is decarbonization. Touch on this on the last slide. As efforts to keep, or as efforts to decarbonize become more and more common, it's more attractive to keep the nuclear plants online. So there are also a few major benefits of modernization directly to the utility. I think I got muted. Can you guys hear me still? Okay, perfect.
Yeah, that was my error.
Okay.
I'm sorry.
No problem. No problem. Just making sure. So some of the benefits directly to the utility are more efficient use of personnel time and labor. So automating processes, streamlining processes, and eliminating some tasks using modernization can help to save personnel time. And then they can go do other things at the site and other high priority tasks. Modernization can also result in increased reliability for plant systems and components. As an example here, advanced inspection techniques can help to identify an issue in a component like a pump before it becomes a failure problem. Third here, improved plant performance and outage performance. Touching on outages, nuclear plants go into outages for component maintenance and fuel loading on a routine basis. And outage efficiency is an ongoing focus area for the industry, so the team can get the reactors back online and producing electricity as soon as possible. And there are some modernizations that help to make outage execution more efficient and outage planning more efficient as well. And last listed here, but certainly not least, is increased personnel safety. So minimizing or eliminating or replacing tasks with modernized improvements can help to decrease the risk of industrial and radiological, or the instances of radiological and industrial risks. That improves safety for those who work at the site and then also contractors who happen to be on site. So now that we have a 10,000-foot view of modernization, I did want to dive deeper into a few different modernization topics that are being implemented or piloted at nuclear power plants. So the first I wanted to cover here is robotics. Robotics are a great method or an alternative to executing manual tasks that are done by a human. Robotics actually have a pretty long history of applications in nuclear power plants. They've been used since the 1970s timeframe with helping with cleanup at TMI-2. Despite that pretty long history, robotic usage historically has been pretty limited to specific one-off tasks, but this is beginning to change and advance as robotic technology advances. So with that, some robots or some utilities are beginning to purchase more general purpose robots that they can deploy on an as needed basis. One specific example of that is the Spot robot, which is a Boston Dynamics robot that's become pretty popular in the nuclear industry. You might have seen some videos of this robot walking around. It kind of looks like a dog walking around. Implementation of robotics is most useful in plant locations that are either not accessible to humans or that are hazardous for humans to enter. So this slide covers a few different robotics types that are available for use. The top row shows 3 different types of ground-based robotics. So those are robotics that are traversing land and not flying or underwater. All the way on the left here, this is a wheeled robot. It's often the simplest design of robot. The middle one is a tracked ground-based robot. So compared to a wheeled robot, the tracked ones have a tread and are able to better navigate going up an incline or navigating more difficult terrain. And then here on the right, there's an example of a legged robot. So these are often the most complex design of ground-based robotics, and they're able to walk on their legs, and most are able to climb upstairs, which makes them pretty versatile. And then on the bottom here, here we have a picture of an example picture of a drone. So those are flying robots that can fly and reach those hard to reach areas. And lastly, submersibles. So those are swimming or underwater robots. So there's a lot of different types of robots, but which one you choose depends on the specific application that you would be using it for in a nuclear power plant. Most robots can be controlled by an operator, so using a remote control, or function autonomously. And that means that they have a pre-planned route that is directed and they go without remote control operation. To help with specifically with autonomous operation and also remote controlled operation, many robots contain sensors that can help them avoid obstacles, to avoid running into something. That is particularly helpful again with the autonomous operation where the robot is not actively being controlled by a person. It's pretty cool to have robots at a nuclear plant or at any utility, but without the proper tools installed on the robot to do things, their usefulness is pretty limited. So that's where payloads come into play. Payloads are those different tools that help you actually carry out a robotic mission. And some of the common ones that are used in nuclear power plants are cameras for capturing pictures and videos. So at the bottom here, you can see a drone that has looks like a red camera attached to it for taking pictures and videos. Another type of payload is an arm attachment. So this can grip things. This can be used for task execution, like turning a knob on a door or turning a valve. So you can see at the top here, this is the spot robot I talked about earlier with an arm attachment. It looks like it's moving looks like a vacuum to me, but I'm not exactly sure. Looks like it's gripping a vacuum and it's able to move that. Another type of payload that's commonly used is different testing equipment, such as a UT or ultrasonic sensor that can be used to test material thickness. UT sensors were traditionally used by a human holding the sensor, but now can be used by a robot instead. So the most common use case at nuclear power plants is currently visual inspections and component testing in those hazardous or hard to reach areas. There are some other use cases such as maintenance, rad protection, common routine surveillances, and then other physical task execution like cutting a pipe. The bottom pictures here highlight a few different use case examples based on the different robotic types we touched on earlier. So first we have a picture of a containment structure. Containment structures are those large concrete domes that are surrounding the reactor. These things are really big. They're over 200, they can be over 200 feet tall and 100 feet in diameter. And nuclear sites are required to go in or go outside and inspect the internals and externals of these containment domes at a fixed time frame. This presents a really good use case application for drones where they can fly up and do those visual inspections rather than sending a person up to that high height and do it manually. A second use case in the middle here is ground-based robotics for radiation surveys. So the site's rad protection team is required to go in different areas around the site and take manual readings of radiation levels. Robotics can be equipped with dosimeters and other radiation level reading equipment and sent in place of humans to go and take those surveillances. So this is a really good use case because it can help to save time for the rad tech and then also can save the personnel saves personnel time and dose from entering in those high radiation areas. And then on the right here, it's a picture of a submersible. So submersibles can be used for intake structure inspections and debris removal. So the water is the coolant in our US nuclear power plants, the commercial ones anyway. And water is taken in from lakes and rivers and other natural water bodies. They're taken in through this intake structure, which has a screen to screen out any debris or fish or anything else that might be in that water. And that intake structure is required to be inspected, again, at some set interval. Traditionally, this is done by a human diver, but diving can be dangerous and it can be extremely expensive. So there's a good business case for using a submersible with a camera equipped on it to go and do those intake structure inspections instead of hiring and deploying a diver. So this slide covers just kind of summarize everything, summarizes some of the benefits and challenges associated with robotics. I've covered a number of these benefits on the last couple slides when we talk through use cases, but I'll summarize them again here. So first, increase personnel safety. So this is achieved by reducing exposure to industrial hazards like high heights, heat, or even confined spaces, and then also reducing potential radiological exposure. Robots can also help to reduce the costs by eliminating manual labor and preventing unplanned downpowers. So I'll touch on that a little bit more. Sometimes manual inspections may require the plant to reduce power so that a person can safely enter a given area on site. And if a robot is sent in instead of a person, that may help to avoid that power disruption and keep the plant running a normal operation. And then lastly here, improved task execution. I can touch on an example. If a robot is able to collect additional data, since they can reach different areas and stay longer in certain areas, that can improve the amount and quality of data that is collected from that task. So there are a lot of benefits of deploying robots as a modernization improvement, but this also comes with a few different challenges I wanted to touch on. The first is cybersecurity. So if a robot is collecting data, want to make sure that that data is secure and handled appropriately. The second is collision risk. So one of the key concerns that utilities have about adopting robots is that they could collide with important pieces of equipment and cause something to break or cause harm to a piece of equipment on site. Things like that collision avoidance and obstacle avoidance, those features should be helpful for kind of quelling that risk. The third one is actually a regulatory requirement. So the Federal Aviation Administration, or FAA, has a requirement for outdoor drone use in the FAA airspace, that if drones are flown outdoors, the operator must have line of sight, or it must be able to see that drone at all times. And so that can potentially limit drone usage, specifically in autonomous applications for that drone. And then the last one I want to touch on is radiological controls. So one concern is that if a robot is set into a plant and becomes contaminated with radiation, it potentially could not exit the plant. It couldn't be used again in other outside the radiation zone. So some personnel are worried about a potential waste of an investment. So you purchase an expensive robot and then it becomes contaminated. Using the site's tool radiation procedures, you should be able to mitigate that concern as well. So the next modernization topic I wanted to touch on is online monitoring of equipment. So to give some background, operators on site routinely perform rounds to collect different measurements of equipment parameters. There's an opportunity to modernize this activity with online monitoring. So online monitoring involves installing permanent sensors on pumps, motors, turbines, or other equipment to collect data and then transmit that to some sort of central computer. At many utilities, that data that is collected is sent to a central repository called a Monitoring and Diagnostic, or M&D Center, with dedicated staff who take a look at the data that's incoming. So if an issue is identified, if a trend looks like it's an adverse trend is identified, the dedicated staff will take a look at it and determine if any action on site is needed. There's also an opportunity to use some AI and machine learning with advanced pattern recognition models. So this is some software that can identify trends in plant data and make predictions for equipment health. And this trending of data and prediction can help the site transition from what's called time-based maintenance to condition-based maintenance. In a more traditional time-based maintenance scheme, the site goes in and inspects a piece of equipment at a set time interval So say for a given valve, the site has to go in and inspect and perform maintenance on this valve every 2 years, regardless of if this valve has ever had any issues, a history of any issues in the recent past. But with condition-based maintenance, the site can use the actual condition of that equipment to make informed decisions on what maintenance and inspections need to be performed. This helps to eliminate potentially unnecessary inspections that can save time and money and avoid going in and touching equipment and causing other issues. This also helps to put resources that would otherwise be spent on those time-based maintenance activities to higher risk equipment, which is really important, especially during outages when that efficiency factor is key. Again, here I wanted to just highlight some of the benefits and challenges of online monitoring. Covered some of these benefits already with some of my on the last slide, but one of the major benefits is reducing the amount of manual labor with operator walkdowns, and potentially reducing maintenance and staff labor by extending inspection intervals or potentially eliminating those inspections altogether. Online monitoring can also provide more frequent data and higher quality data, which can increase the site's awareness of equipment health, and in turn helps to avoid equipment failure through that earlier detection mechanism. Some of the challenges with online monitoring include wireless bandwidth and coverage. So when you use these sensors, you're collecting a lot more data, you're transmitting a lot more data compared to traditional methods. So the site's wireless coverage, so where in the site that Wi-Fi is available or other wireless protocols are available, and the bandwidth to support that data transfer must be ready before you can effectively install this equipment. And then similarly to robotics, cybersecurity is another concern, making sure that the data that's collected and transmitted is secure. And then lastly, I wanted to touch on kind of bridging the gap between just collecting data and then actually using it. So it's one thing for a site to put sensors all over and collect a lot of data, but you will not actually reap the full benefits of that improvement, that modernization, unless there's the kind of like the mechanisms in place to actually use that data for decision making. So overcoming that challenge can be both a personnel mindset shift to data driven decision making and plant process changes. And the last modernization upgrade I wanted to touch a little bit deeper on was digital instrumentation and controls, or digital INC. So INC involves measuring and controlling plant process variables, like controlling process flow through a given route, temperatures, levels in tanks, and things like that. So the US fleet was originally built with analog control systems, which are considered the older and legacy equipment. The aging components have some obsolescence risks with like discontinued vendor support. So there's an opportunity to modernize with digital INC, which uses computers to process signals. Digital INC is pretty widely used across other industries and has more recently been incorporated into the commercial nuclear sector more commonly. So some of the benefits of digital INC is, like I mentioned, there's more vendors available with the new technology, potential to increase the reliability and accuracy with new technology, which it can in turn improve plant operation. Also, many digital control systems come with self-diagnostic capabilities, so potentially helping you to identify issues in real time. And then lastly here, since digital INC uses computer systems, they are implementing software, which allows a bit more flexibility with the control system software. There are also a few key challenges associated with digital INC. Digital INC and changes tend to be some of the most expensive modernization improvements. They're really high cost, but also high benefit improvement for the sites. And similar to the other modernizations, the common theme here, cybersecurity needs to be appropriately considered and controlled when transferring from analog to digital INC. Licensing is another challenge, making sure that the system functionality is retained when transitioning from one INC type to another. And then last here, software incorporation can lead to new potential failure modes that the site will need to consider and mitigate. And then just wanted to explain this picture here. So this is a more digital control room. So with digital INC comes the opportunity to modernize part of or do a complete overhaul of the main control room. So that's just another tidbit. It's not really I wouldn't say it's a benefit or a challenge, but the opportunity to change how the operator interfaces with the control room. So just also wanted to take a moment to touch on a few modernizations that are being considered in the industry and piloted. So the first one up here is advanced fuel. So accident tolerant fuel introduces new materials into the fuel pellets or the cladding layer to help improve operation and make it more accident resistant. So materials like chromium can be coated on the outer cladding layer that can increase the fuel's resistance to things like oxidation or debris. Materials can also be doped into or mixed basically into the fuel pellet during manufacturing, which again can reduce the risk of damage to the fuel. And there are some vendors that are also exploring increasing the maximum enrichment of U-235 in fuel from 5% to 10%, I believe. And increasing this enrichment level could help to save the plant money on having to purchase fewer fuel assemblies, and can also help the reactor achieve higher burnup, which would allow the reactor to operate for longer fuel cycles. So they have to go offline and refuel less frequently. And then the second more upcoming technology, potential upcoming technology, is using nuclear for clean hydrogen production. So hydrogen is a pretty attractive fuel source for transportation and industrial applications. Hydrogen is considered clean because of fuel cells byproduct is water. So it's not releasing any greenhouse gases there. Nearly all commercial hydrogen production is currently produced through something called steam methane reforming, where natural gas is heated with steam and hydrogen is produced. Through this process, greenhouse gases are released, but hydrogen can also be created through a process called electrolysis. So this is where water is split using electricity. The electrolysis process itself doesn't release any greenhouse gases. So this is an area where nuclear could potentially come into play. Electricity produced from nuclear fuel without those carbon byproducts could be used to power electrolysis and produce what's called green hydrogen. So the industry is considering demos of electrolyzers at nuclear power plants, and also considering the development of hydrogen hubs. These are networks of hydrogen producers, hydrogen consumers, and then the infrastructure necessary to connect those producers and consumers. So now that we've gone through some of the exciting examples of modernization, I did want to touch on how is wide-scale modernization actually feasible, and what are some of the enablers to making modernization possible? So one of the first enabler to talk about is life extension plans. So many utilities are considering extending their license for operation so so their units can continue to operate for longer. These strategies often rely on equipment upgrades, which presents an opportunity to sync modernization improvements with with those life extension strategies, and that can help to improve the business case for modernization when comparing it to just performing the modernization improvement alone. Fleet extension also improves the business case for modernization since the utility will be, in theory, operating for longer, so they can recoup the benefits of those investments for a longer period of time. The second main enabler here is there are several state and federal policies that are providing credit or revenue to nuclear power plants. So this additional revenue can help to preserve the fleet and may provide some additional financial flexibility. So I've listed a few recent policy changes here. So the first one is the Inflation Reduction Act, or IRA, which was recently passed. And the IRA provides tax credit to existing nuclear and other clean energy technologies. The bipartisan infrastructure law provides credits to plants that are actually projected to prematurely close due to financial concerns. Third here, the state zero emission credits, or ZECs. This is on a state level where several states, I believe it's a few are New Jersey and Connecticut, among others, provide additional energy or provide additional revenue for producing clean energy. And then similar to the federal government with their carbon initiatives, carbon reduction initiatives, there are several states that are going carbon free by a certain target date. This makes the case for a utility's investment in their nuclear assets as compared to some of their other assets like natural gas and coal. And then last listed here, there are several pilots that are being funded by the government, specifically by the DOE, that can pilot new technologies like the advanced fuel that we talked about on the last slide, and also some control upgrades. Another enabler of modernization is industry peer groups and other industry resources. The nuclear industry is a pretty unique industry in that the utilities are often willing to share their best practices and lessons learned with each other. So there are several working groups and utility groups for modernization initiatives to help promote new technology and new modernization use cases. And then lastly, there's currently a lot of research going into advanced nuclear power technologies and deployment. So new technology and new licensing strategies that are being used for advanced reactors may be able to be transferred and benefit the existing fleet. And then there's also obviously a lot of challenges to modernization. The first being that modernization often involves a significant investment, and there are often competing site priorities for those resources. So for example, it could be challenging to divert labor or financial resources to these more forward-looking modernization projects when you have these near-term pressing issues like a pipe crack or something like that, that will imminently impact operation. Another challenge is in licensing. So first of a kind improvements that may involve licensing changes can be timely and costly. So that has been a barrier to modernization. And then in general, challenges to the nuclear power sector, just general challenges may also impact how modernization shakes out. So one challenge currently facing the industry at large is the nuclear workforce. So the workforce is facing a shortage in skilled trade. Those are things like welding and electricians, and then also in engineering staff. And this issue will potentially become even an increasing issue because of the advanced nuclear deployment. We're going to need even more resources and more staff in order to support both the existing nuclear and advanced nuclear industry. And then one of the longstanding challenges that I'm sure a lot of people on this call are aware of is public awareness of nuclear power. So there's been pretty varying public opinion of nuclear power since the onset of nuclear power generation. But luckily there are a good amount of nuclear advocacy and education resources to promote and educate people on nuclear power operation. So I've listed a few here, including Nuclear Matters, NEI, and then one of the groups I'm involved in is Women in Nuclear has some resources for advocacy as well. So I think that's all the content I had, but wanted to open up and see if anyone had questions or things to discuss based on what I've talked about here today.
That's terrific. Thank you very much, Melissa. That was really very thorough and great. And I'm sure everybody got a lot out of it. So I don't have anything in the chat yet, but maybe we can open up people's mute buttons. And there's over 50 people here, so I'm sure there's questions.
Is there any modernization in terms of like waste disposal? Nuclear waste.
And you know,
Yeah.
it'd be great if you could announce your name and where you're from, and then the question, so it gives Melissa a little relevance as to where the question is coming from.
Oh, I'm taking engineering 98. I'm an undergrad studying physics and economics.
Excellent, thank you.
Yeah, so that's one of the common questions with nuclear is what do we do with the waste? So there are some modernizations in terms of looking towards advanced fuel recycling. So being able to reprocess and recycle fuel to generate new fuel to be used. That's being done abroad, and the US is also starting to look at those technologies as well.
Any other questions? There's got to be more student questions. This was really good this is a good thorough overview. I really enjoyed it. It was good. I think everybody's shy today. So tell us where the from a service-based industry, from your perspective, where's the technology headed now? I know there's a lot of new companies out there. They're in actually like round C and D funding phases. There's a ton of, you know, and I've seen our senior vice president, Neil Wilmhurst, talk about supply chain and, you know, keeping a focus on the supply chain is very important, because at some point in the future, when we do look at some of these new technologies, it's going to be very intensive on maintenance, parts, and even life extension of some of the older. You saw maybe recently in the news about 2 weeks ago that Diablo Canyon was extended by Governor Newsom. That was a big battle a couple of years ago where they did a 180-degree reverse on their stance on that, but that makes up 23% of the capacity in the state of California. So maybe seeing some more. So what does it mean for you and your service company? How's your outlook right now from a technology standpoint, from a service standpoint, and where do you see things going?
Yeah, so I can touch on a few pieces there, and it is really exciting that the news on Diablo Canyon also mentioned the Palisades news. Palisades is a nuclear power plant that was actually shut down a little over a year and a half ago now, and they just announced that they'll be reopening or trying to reopen as well. So that's really exciting news in the industry. Totally agree that supply chain and, like I mentioned, workforce concerns is something that will need to be mitigated. In terms of supply chain, understanding what your nuclear's long-term strategies are and their overall like long-range plans, and having that plan in place in order to place orders as soon as possible is going to be really important to help make sure that you have the equipment needed for replacements or for new technology as soon as feasible. And you had also touched on, hey, where is modernization going next? Something that has been covered a lot in, or is really coming to light in the industry is AI and machine learning. That's probably some buzzwords that everyone's hearing all in various industries, but AI and ML is definitely being considered a lot in the nuclear industry, and there's a lot of different research going on for that as well. So it's one of the areas where I think that things are shifting towards.
Yeah, that's good. Yeah, I just also wanted to mention that in the Inflation Reduction Act, which was passed, there is a tax credit in there for zero emissions, which really brings nuclear into the new age of tax credits to advance it. And then also in the Inflation Reduction Act, there is a tremendous amount of nuclear training coming up. So that's going to be really a key driver towards nuclear power. And then they also have in the Inflation Reduction Act funding for high assay, low enriched uranium. And that's about $700 million of development going forward. So there's quite a bit of horsepower that's behind that. And then, of course, it's not so much in the Infrastructure Act, but for students and those who are looking at it, you know, this is a huge pivot in where the modernization of the grid will occur from a low carbon emission standpoint. So your talk is very timely and it was very much appreciated. Any other questions?
Well, there's a question in the chat box from Joe Andrusani.
Great.
What percentage of plant operating costs does maintenance typically represent, Melissa? What percentage of that maintenance budget is going toward modernization strategies, and how fast is it growing? So the three-point question.
Yeah. So I would say that modernization budgets typically, and this changes from plant to plant, it seems to be a separate bucket of funding than from the maintenance bucket of funding. So it's not necessarily taking away any maintenance funding, but utilities are commonly planning for modernization improvements and setting aside funding to pilot different improvements. And I would say that it's becoming a lot more common for different utilities to have programs dedicated towards innovation and modernization technologies. So I'd say it's growing in popularity. There's different site group or utility working groups to focus on modernization, but it's not necessarily taking money away from the maintenance program in general. In terms of percent of plant operating costs, I don't know that number off the top of my head. There's probably some people online that are from utilities. So if anyone has a better idea of the percentage there, happy to take that input.
It was good. Then
Another question
Tom,
in the chat box on cybersecurity. Seems to be a big challenge with deployment of much digital equipment.
Yep.
How is the industry addressing cybersecurity? Tom, what was that question?
Tom W.
Yeah, so exactly right. Cyber was brought up in all three of those more detailed modernization technology examples that I walked through. It's definitely a big concern and hurdle in the nuclear industry. So the utilities seem to be developing different cyber programs to consistently approach cybersecurity and set up procedures for making sure that there's appropriate data isolation and strict controls over how different computers and laptops are used. So yeah, they're setting up programs, setting up procedures, and appropriately isolating data so that can't be either hacked or used in an adverse way.
And then Joe Andrisiani, are these advanced maintenance technologies being designed into new nuclear reactors like small modular reactors?
Yeah, it's a good question. So small modular reactors are a little bit different than the large scale reactors in that they're designed to be fueled and operate without as much maintenance. So in that respect, they're using kind of the more modern maintenance technologies more inherently than what the commercial fleet today is doing. But there are a lot of crossovers in terms of taking the sort of the advancements that are being used in the advanced nuclear industry and trying to apply them to the commercial nuclear industry.
Great.
Are there cons for those compact reactors, like as opposed to what are the pros and cons of creating one of those instead of a bigger reactor?
Yeah, that's a good question. So the advanced nuclear reactors, especially the SMRs, are smaller. So I think they're a maximum of about 300 megawatts. So their use cases are different than the commercial nuclear reactors, which are really big reactors. So for an SMR, a small modular reactor, those are built to be deployed in potentially remote locations where I think the common example is, hey, up in Alaska, where you don't have the huge infrastructure for transmission and distribution of energy, you can go in and place a small modular reactor there, and it can power a local community that doesn't need as much power as a 1,200 megawatt reactor. So I would say I don't know if this is a con, but it's just there's a smaller output for it, but that's also a benefit in terms of its modularity and ability to put that in different locations.
So I'm sure it's the output smaller, but is like the cost per megawatt higher or something like that for
so there's still nuclear reactors are still being designed. So I think that in any new technology, there's some upfront design cost that can increase cost, but as small modular reactors become more common, I think their price point will decrease.
I think there's one last question, and I think we're going to wrap up. Let's see, it says, Tom W. had another question. You said only 93 reactors and 54 plants today. Any plans for more plants and reactors?
Yeah, so in terms of large scale commercial reactors, Palisades restarting, like I touched on, that's a big one that might come back online. People are starting to think about building larger scale reactors, but there's no other commercial nuclear reactors that are under construction other than Vogtle Unit 4 at this time in the US. Abroad, especially in Asia and China and India, there's a lot of reactors that are currently being built. So people are building in the US, the only current one under construction is Vogtle. And then there's obviously, like I touched on, the advanced reactors are starting to be designed and demonstrated in the US as well.
Excellent. Okay, well, thank you, Melissa. That was really great. Susan posted that the next Energy Systems seminar is on February 5th with Dr. Noble from EPRI on decarbonization pathways, how dispatchable gas turbines are critical for our energy trilemma. So the registration is there in the meeting notes, and if you want to be on the list, I guess, Susan, how can they get in touch? You send you a note, or is there a link anywhere if they want to pass this on to somebody? Oh, there it is. Oh, I see it there. There's a link right there.
Yeah, once the two links for the info session and for the next seminar are both in the chat box. Once they register and they get on, and I send them a Google invitation, they can forward it on to anybody, or just forward the registration, preferably with the registration form, because that way we can see who's joining in on the seminars.
Great. Okay, well, thank you. It's been a really good talk. Thank you, Melissa. We appreciate it. And thank you to everybody in attendance. And we look forward to seeing you on the next seminar series. Thanks, Rudy, again for co-hosting, and thanks for this opportunity. Melissa, thank you again, and we'll see you soon.
Thank you,
All right.
everyone.
Thank you.
Thank you.